Hello, I am Pujanjali Shukla of Isabella Thoburn College, roll number 205047. Introduction. So, what is equilibrium? Equilibrium means a state of balance, especially between forces or influences that are working in opposite side or ways. A structure is in equilibrium when all the forces or moments acting upon it are balanced. This means that each and every force acting upon a body or a part of the body is resisted by either an equal and opposite force or set of forces whose net resultant is zero. Now, what are the conditions of equilibrium? The first one is the sum or resultant of all external forces acting on the body must be equal to 0. The sum or resultant of all external torques from external forces acting on the object must be 0. Now, type of equilibrium. There are two types of equilibrium, stable and unstable equilibrium. When the body moves on a smooth curve which is shown by the figure given below, it takes the different position A, B and C. It will rest at points A, B and C, which are the position of minima and maxima of the curve. If the body is slightly displaced from the position of rest, that is A and B, then it will try to come back its original position of rest. Here the equilibrium of body is stable, whereas it is displaced from the position at B, then it will try to go further away from the original position. Here the equilibrium of a body is unstable. In a rotational mechanical equilibrium, the angular momentum of the object is conserved and the net torque is zero. Now, stable and unstable equilibrium. So, what is center of gravity? It is a point at which total weight or mass of a body supposed to be concentrated is known as center of gravity. In 2D dimension, that is two dimension, in case of a plane is known as centroid. The point of contact and the center of gravity of body lies in the same line. Now, what is center of gravity of different surfaces? The center of gravity of sphere whose radius is a is at a distance a, as you can see from the figure. D is equals to a, that is at the center of sphere. Second, center of gravity of hemisphere of radius a from the flat surface is at distance of 3 upon 8a. Center of gravity of hemisphere of radius a from the central surface is at a distance of 5 upon 8a. Fourth, the center of gravity of cone of height h is at a distance of h upon 4. Now, the center of gravity of cube of radius a is at a distance of a upon 2. Now, what is the center of gravity of two combined bodies? Let G1 and G2 are the centers of gravity. This is G2 and this is G1 of lower and upper body having weight W1 and W2 respectively. Let G is a point where total weight of combined body lies, that is A is central gravity of whole body. Then AG is equals to AG1 W1 plus AG2 W2 upon W1 plus W2, where W1 and W2 are the weights. Now, what is stable and unstable equilibrium? If a body is in equilibrium under direction of system of forces or slightly displaced from its position of equilibrium, then it is may remain in equilibrium its position or try to come back to its original position of equilibrium, or may have the tendency to move further away from the position of equilibrium. These cases respectively known as neutral, stable or unstable. Now, stable or instability of a body with its center of gravity. In case 1, you can see there is a slightly displaced from the center of gravity. Case 2, it is again slightly displaced from the center of gravity. This is the condition of neutral. This is a condition of stable equilibrium, and in the third one you can see the center of gravity is above, that is it is a case of unstable equilibrium. Here we discuss case of sphere. Case 1, if the center of gravity lies on the vertical line to the point of contact, that is it is below the geometrical center, it is a condition of stable equilibrium. Because of it is slightly displaced from its position of equilibrium, it tends to come back to its original position of equilibrium due to the less of the turning effect. As you can see, the center of gravity has come here. Now, case 2, If the center of gravity lies on the vertical line to the point of contact and it is above the geometrical center, then it is a condition of unstable equilibrium, because if it is slightly displaced from its position of equilibrium, it tends to go away from its original position due to more of turning effect. As you can see in this, the center of gravity has gone above. Now the third case, if the center of gravity and geometrical center of the body coincide at a point, then there is no turning effect. Then it's condition of neutral equilibrium. In neutral equilibrium, there is no turning effect. And in unstable equilibrium, there is more of turning effect, and in stable equilibrium, there is less of turning effect. Now, energy test of nature of stability. In position of equilibrium of a body under the system of conservative of forces, the potential energy is either maximum or minimum. If potential energy are maximum, then the equilibrium is unstable. If potential energy are minimum, if it is minimum, then equilibrium is stable. If potential energy is maximum, it is unstable, and if potential energy is minimum, it will be stable. That is dz upon d theta is equals to 0, where theta is equals to 5, 1, 5, alpha 1, alpha 2, alpha 3. If d2z upon d theta is greater than 0, that is minimum, then it is a case of stable equilibrium. And if d2z upon d theta square is less than 0, then it is a case of unstable equilibrium, because it will be maximum. Now test for the nature of stability under its height or weight. Suppose a body is in equilibrium under its weight. We know that a stable equilibrium center of gravity must have minimum height, whereas for the unstable equilibrium center of gravity must have maximum height from fixed horizontal plane, position of rest, that is. Let z be the height from the horizontal plane to the center of gravity. It is a term of theta, that is z is equals to f theta. For the position of rest, dz upon d theta is equals to 0. We get some value of theta is equals to alpha 1, alpha 2 or alpha 3. Case 1, if for any value of theta d2z upon d theta square is greater than 0, then z is minimum. Then it is a condition of stability. And in case 2, if for any value of d2z upon d theta is greater than 0, is less than 0, z is maximum, that is, it is a condition of unstable equilibrium. Test for stability of a body resting on another. If the body is at rest in equilibrium upon another body, the position of two bodies in contact is fair. Here r is the radius of lower body, small r is the radius of upper body, and h is the height from point of contact to the center of gravity of the upper body. Then, if it is equilibrium is stable, then 1 upon h is greater than 1 upon r plus 1 upon r, and if equilibrium is unstable, then 1 upon h is less than 1 upon small r plus 1 upon capital R. Now, the third topic is application of theory of equilibrium of system of forces. When architect or engineer design building, they have to make certain that all forces, both rotational and translation, are balanced. When we build a structure like a bridge or a house, we try to balance all the forces in each part of the building. We have to make sure that all the translation forces sum to be 0. So some part of the building doesn't move from one side or up and down. We have to make use that of center force doesn't cause some part of the building to twist or rotate around the another point. Now point sort central axis. You can see the figure in this. A line through a rigid body which is parallel to the vector sum f of the system of forces acting on a body and which is located to that of the system of forces of equivalent to the forces F applied anywhere along the line plus a couple where torque is equal to the component of the total torque T exerted by the system in the direction of F. Now, application of theory of equilibrium of strings. You use the string on your handbag to lift it and carry it around. Depending upon the weight inside the bag, the amount of tension in the string also varies, and eventually when the load exceeds the load carrying capacity of the string, it breaks. To make it more interesting, consider then the two strings on your bag are of different length and the bag is quite heavy, so you take the help of your friend to pick it up, each holding one string. To avoid the bag from touching the ground, you and your friends would be at the different distance and from the bag. Taking your hand level as reference of the person that is closer to the bag would have to apply more force. Thus, that string would have more tension in it. This simple concept of equilibrium of string can be expanded to generate a complicated system as well. You observe its application in the cable machine exercise at the gym. Now, the equation of common catenary. You can see the figure. This distance AB is called span. Distance CD is sag. Distance CD is called span. Sag in the middle. Arc CP is equals to S. C is equals to C, and weight per unit length is equals to W. Let ACB be the string of each. The lowest point is C, P. P is any point on the string such that the length of arc CP is equals to S. Let T be the length at any point P and psi its inclination to the horizontal. At the lowest point C, the tension is horizontal and let it be denoted by T naught. Let W be the weight per unit length and linear density of the string, which is constant throughout. As the string is uniform, then the portion Cp of the string is in equilibrium under the action of forces, which are: number 1, the tension at P and T naught at C. The weight Ws acting along a vertical line passing through the center of gravity of the portion Cp and through the point where the two tensions meet. All these three forms will meet at one point for the string to be in equilibrium. Resolving these forces horizontally and vertically, T naught is equals to T cos sigma psi, we mark as equation 1. Ws is equals to T sin psi, equation 2. T naught is equals to Wc, so T cos psi is equals to Wc, and dividing 2 by 3, tan psi is equals to S upon C. So S is equals to C tan psi. Now the last topic is application of theory of equilibrium on virtual work. So what is virtual work and principle of virtual work? So what is virtual work? Work is equals to force into displacement, that is W is equals to Fd cos theta. Now if 0 is greater than or equals to theta and is greater than less than 90 degree, then work done is positive as cos theta is positive. If 0 is greater than theta and is less than or equals to pi, then work is negative as cos theta is negative. That is, if the work is positive, the direction of forces and the direction of displacement are same, and if the work is negative, then the direction of forces and displacement are opposite. Now what is the principle of virtual work? So what are the necessary and sufficient condition is that particle or rigid body acted upon by the number of coplanar force to be in equilibrium is that the algebraic sum of the virtual work done by forces during any small displacement consists with geometrical condition is 0. That is, body is in equilibrium if the sum of the work done by the force for small displacement is 0. That is, sigma Fz is equals to 0. Sigma Fv is equals to 0 if and only if sigma W is equals to 0.